All right, my friends, I hope that things didn't go too tough on you for 2006 Form A number 5 here. Before we get going, you'll see definitely some Taylor series action here in Part C. So just a quick review, the Taylor series for a given function centered at x equals c, we could say that a given function can be approximated by. And so let's think about what were the terms of this Taylor series. The first term would have been this function, the given function, evaluated at exactly the number you're centering it at. And then, oopsie. And then your first degree term would be the derivative of the function you're approximating evaluated at your central value. And then you can see an evidence of being shifted to the right C units here and on your linear term. And then when you start getting out to the second degree term, you can see evidence of factorials needing to be there. Oops. And you could theoretically go forever. If you stop at a certain term, then you'd have a polynomial of a certain degree. So for example, in this example, they have you stop at degree 2. And then you could go ahead and use the same notation, or you could call it p sub 2 of x like we have in the past. And they wouldn't care really about what notation you use. Okay, so let's go ahead and get started on it. The introduction says, consider the differential equation dy dx equals 5x squared minus 6 over the quantity y minus 2. Let y equal f of x be the particular solution to this differential equation with the initial condition f of negative 1 equals negative 4. Part A, evaluate dy dx, and the second derivative also at negative 1, negative 4. So let's get started on that. Part A, I'm just going to go ahead and write down what they said dy dx was equal to. And then they want us to evaluate that at the point negative 1, negative 4. And that would be very simply just plugging in negative 1 for the x and then negative 4 for the y. And then simplify that. You've got 5, what is that, plus 1? And so I believe that you'd have it. Okay. And then they also asked you for the second derivative evaluated at the same point. So for that, let's go ahead and point out that d squared y over dx squared is d dx of dy dx. You do not have to show all these steps. This is just for explaining purposes. And then that would be d dx of that given differential equation. So then now let's go ahead and take the derivative. Remember, you're taking the derivative with respect to x. So d dx of 5x squared is 10x. Thinking of this fraction as 6 times y minus 2 to the negative 1 using power and chain rule, you'll end up with, I believe, plus 6 over the quantity y minus 2 squared, but then times dy dx. Okay, so that's a general rule for the second derivative. Okay, so now let's go about evaluating that at the point negative 1, negative 4. So we'd have 10 times negative 1 for x plus 6 over negative 4 minus 2 squared. And then what to do about this dy dx? And there's a variety of things that you can do, but I think the quickest thing to think about is that you just really need to figure out what is dy dx at the point that we're evaluating things at. So simplifying as I go, let's see, that's negative 10, what's that, 1/6, I think. And then we had already figured out what dy dx at the point negative 1, negative 4 is. We did that right here, and so you could substitute a 6 in. It looks like the answer here is negative 9. There you go. Okay. There we go. And we're done with part A. Okay. Now let's move on to part B. It says, is it possible for the x-axis to be tangent to the graph of f at some point? Explain why or why not. So let's look at that. I usually kind of get started by explaining. So let's go ahead and do that. So let's think about this. If the x-axis is tangent to the graph of f at a given point. And you wouldn't have to explain it just like this, but let's say that it's at this x value equaling a. Then, and you wouldn't have to draw a picture, but let's just say, like, you've got here's the x-axis, here's the y-axis. Let's say this is f, boo, boo, boo. And then, okay, there's a little place, maybe this is x equals a. Well, what would have to be true there? Two things. Number one, what's your y-coordinate since you're on the x-axis? Boom, it's 0. And second of all, what's your first derivative at that a value since it's also tangent? Boom, 0. So basically what I'm going to say is then f of that value would have to be 0, and f prime of that value would also have to be 0. And then the word simultaneously is totally redundant, but I still kind of like writing it. Okay, so let's look at that. What's a relationship that has, this is the y-coordinate, and then this is the derivative. So I claim that this given function here is a perfect relationship for this function between those two things. So dy dx at the place where x is a would be 5 times a squared minus 6 over, and then you could actually, instead of saying just x equals a, you could say it would have to be at a0 since it's on the x-axis. So you could do 0 minus 2. Okay, so let's look at that. So that says 5a squared plus 3. Okay. And there are a couple ways to explain yourself. You could actually notice right here that unless a becomes an imaginary thing, and it's not supposed to, so as long as a is real, you square it, you can't get anything negative. You're going to multiply that by a positive 5 and add 3. So one way to finish this out would be to say, hey, look, this is greater than 0, which means it could never equal 0. So these two things could never happen simultaneously. Let's say that you are, plugging and chugging along and you don't notice that you can be done already. Then you could actually go ahead and say, okay, well, I want this to be 0 as well. And then you can just go through the motions of solving for a, and then you'll find out that a has to be imaginary. And that, I would hope, would be your big trigger. So let's say you didn't notice that this right side, can never be 0, and you're just solving along. You could subtract the 3 over. Maybe about here you start noticing that this isn't going to happen. This side can never be a negative like the left side. But if you don't notice, you could do this. And if you don't notice that this is impossible, then you could square root and obediently remember your plus or minuses and simplify it. And imaginary numbers are here to let you know that this is just not going to happen on a real XY plane. So many places for you to notice that it is not possible for the x-axis to be tangent to the graph of f. You could just leave it at that, or you could say at any given point or whatever you like, but there it is. Okay, now for part C. Part C is definitely a lot more current. It says find the second degree Taylor polynomial for f about x equals -1. So we're going to go to that definition that I mentioned before we got started. And so p sub 2 of x would equal, and we're centering this at x equals -1. So that would be f of -1 plus f prime of -1 times x minus -1 or x plus 1, evidence of shifting something to the left one. So it could be centered at -1. And then plus f double prime of -1 times x minus 1, x plus 1 squared over 2, or 2 factorial. Okay, so, and then this is going to be way easier than it looks, because f of -1 was given to us when they told us, they told you here, and then they also told you here, since y and f of x are interchangeable in this problem. So what are we going to put in for f of -1? Yeah, -4. F prime of 1, we found that in part A. So f prime of -1 is 6. F double prime of -1, we found that also in part A. That's -9. And you are welcome to simplify that, but there's the AP exam doesn't make you simplify things. So if that looks good enough for you, then great. And that's what they wanted for part C. All right, my friends, I hope this helps. I hope you're doing great.